Well, it's 12 o'clock, and good afternoon, everyone. We're going to wait just a little bit, a couple more seconds here. I see we keep having more people come on. All right, well, good afternoon. Thank you for joining our webcast today on Vehicle Assist and Automation Technologies in Bus Revenue Service. This is the third in a series of webcasts sponsored by the Center for Urban Transportation Research. My name is Dennis Heimbaugh, and I'm the Transit Program Director and the Director of the National Bus Rapid Transit Institute here at CUTR. This webcast is being recorded, so in case you miss any part of the presentations today, you'll be able to download that from our website early next week. Let's see. Jennifer, I'm trying to go to slide 2. There we go. A little bit about CUTR, the Center for Urban Transportation Research here at the University of South Florida. On our research program, we have 100 active research projects, about $8 million annually in research dollars, 45 full-time research faculty, and 20 plus students. We're a multimodal focused center with research, training, education, and technical assistance. One of the things we'd like to do before each webinar is ask our audience a few poll questions. It helps us give us an idea of who's here and on the other end of the line. Today's first question is, how many other people are viewing today's webcast with you? So if you just take a few seconds and click on one of those options. Okay, we'll close the polls. And it looks like most people are just by themselves watching this with a few others in the one or two. So for our next question, where are you located? Take a few seconds to wait. Okay, about a third of you are here in the state of Florida, about 45% up in the Northeast, and then some in the Southwest and Southeast, and one person from outside the U.S., so welcome to you. Our final question is, what type of organization do you represent? So we'll open the polling. Okay, we have quite a few from the federal government, some university people, and local government, but a good mix. All right, well, with that, let's get right into the presentation, because that's why you're here today. Our speaker today is Brian Pissarro. Brian is a senior research associate here at CUTR. We lured Brian away from the Florida DOT, where he worked for 7 years at both the district and headquarters level. Prior to that, he was a transportation planner for 3.5 years at the San Diego Association of Governments. He is a graduate of Virginia Tech and the University of Florida and has a master's degree in urban and regional planning. One of his areas of research is vehicle assist and automation technologies, which is what he'll be talking about today. So with that, Brian, take it away.
Okay, thank you for that introduction, Dennis, and thank you everyone for attending this webcast. What I plan to do today is to explain what vehicle assist and automation is, discuss 4 pilot projects that will soon be starting at several transit agencies, and finally share with you some evaluation results of a low-cost form of VAA known as the mechanical docking arm. So let's start by defining vehicle assist and automation. Basically, it's a vehicle guidance system. It can be used to help the driver maintain control of the bus, that's the assist part, or it can automate parts of the bus's operation. In public transit, VAA can be used for a variety of applications such as precision docking, lateral guidance, and collision avoidance. To help you better understand the difference between vehicle assistance and vehicle automation, let's look at an example. The Greater Cleveland Regional Transit Authority uses what's called a mechanical docking arm for precision docking on their bus rapid transit system known as the Health Line. It's a specially designed guide wheel mounted to the front axle. During docking, the driver steers the bus towards the edge of the platform until the guide wheel makes contact. Now, the thing to remember is that the driver controls the docking. By contrast, an example of vehicle automation would be the optical guidance system used by what's called the CUTR bus system in Rouen, France. This system uses cameras mounted on front of the bus that can read the stripes on the road and make steering corrections by comparing where the bus is to where it should be. This docking procedure is automated, although the driver still does control the braking. But as far as steering into the station goes, that part is automated. There's 4 types of VAA guidance systems. First is magnetic. This is a picture of the Phileas bus in the Netherlands. It uses a series of magnets embedded in the pavement along with buses that are equipped with magnetic sensing equipment. Next is mechanical guidance. We've already mentioned Cleveland with precision docking, but another way mechanical guidance can be applied is on a busway. This is a picture of the Oban busway in Adelaide, Australia. It's the world's longest guided busway at 7.5 miles. It uses the same type of guide wheel as Cleveland. However, it has a specially designed track for the buses to run on. The buses can achieve top speeds of up to 100 kilometers per hour on this track, or about 62 miles per hour. And the total width of those 2 lanes that you see in the picture there is about 20 feet. Oops, excuse me. Next type of guidance system is the optical guidance system. This is another picture from the system in Rouen, France. Basically, the way a camera guidance system works is that the cameras look at the stripes on the road and are able to lock onto a trajectory for the bus. And finally, you have GPS-based guidance systems. This is a picture of a test bus that was created for a GPS guidance system that's going to be starting in Minneapolis. Actually, it just started this month, and I'll be talking about that a little bit more in a moment. Now, most applications of vehicle assistant automation have been overseas. In fact, up until recently, there were only 2 transit systems in the U.S. that even attempted to use vehicle assist and automation in revenue service. One is Cleveland, which we already mentioned. The other was the Max Bus Rapid Transit in Las Vegas, which tried to use optical guidance for precision docking at the stations. However, it was discontinued because the cameras had difficulty reading the pavement stripes in the harsh desert environment. However, that being said, there's 4 new locations that will soon be adding vehicle assistant automation to bus revenue service. They include Minneapolis, which just started using a GPS-based guidance system this month to assist with buses that were running on the shoulder. Eugene, Oregon, and Alameda County in California have partnered up with Caltrans and UC Berkeley to develop a magnetic-based guidance system for precision docking and lateral guidance within an HOV lane. And in San Diego, the San Diego Association of Governments recently signed a contract with a vendor to develop an optical guidance system for a new bustle and shoulder service. And I'm going to take a little bit of time to talk about each one of these. Let's start with Minnesota. Minneapolis has a history of allowing buses to run on the shoulder dating back to 1993. In fact, it has a network of over 250 miles of shoulders that the buses are allowed to use when traffic speeds in the general purpose lanes drop below 35 miles an hour. In general, the shoulders are 10 feet wide, and the buses measure 9.5 feet wide from rear view mirror to rear view mirror. That means the driver has half a foot of space between him and the next lane, as you can see in the picture in front of you. And that can be stressful under optimal driving conditions, but it can be even more stressful at night or during inclement weather. So the Minnesota Valley Transit Authority partnered up with the ITS Institute at the University of Minnesota to create what they call a driver assist system that would help reduce bus driver stress while in the shoulder and hopefully encourage the bus drivers to use the shoulders more often, especially during inclement weather. It's a $5.3 million project, and the money is being used to equip 10 buses and to build one bus simulator. The technology is going to be used for lateral guidance within the shoulder and collision avoidance. Like I said, it just began this month. It's a GPS-based guidance system, and feedback is provided to the driver in a number of ways. One of them is through a head-up display, which you see in the picture on the right. Another is a vibrating seat and what's called actuated steering, which I'll describe more in just a second. Collision avoidance, the collision avoidance system provides sensing detection both to the front and side of the vehicle. In the front, the equipment that's used is radar. On the side collision avoidance is provided through what's called LiDAR, or light detection and ranging. The picture in the upper left of your screen is a view through the head-up display. The shoulder boundaries, I'll point them out to you, here and here, are digitally displayed so that the driver can see where the boundaries are regardless of the weather. Objects that could be a threat to the bus are outlined with a rectangle, as you see here. And as the object gets closer to the bus, the rectangle gets larger. The picture below, what you see right here, is what's called the virtual mirror. This is what takes the feedback from the radar and the LiDAR and transmits that information to the driver. So what he is looking at here is a computer screen that simulates 2 lanes of traffic. That little white rectangle here is supposed to represent the bus, and that blue figure to the left is supposed to represent a car in the next lane. Here's how the system works. According to the GPS and digital map, the bus is located here. As the bus starts to move, it may start to drift out of the lane. And a couple of things are going to happen. First, the digital boundary in the head-up display is going to change color to alert the driver that he's starting to drift too far to the left. Next, the driver is going to feel a slight torque on the steering wheel, motioning him to steer in the other direction. And then finally, he's going to feel a vibration in his seat as if he were going over a rumble strip. If he's drifting too far left, the left side of the seat will vibrate. If he's drifting too far to the right side of the seat will vibrate. The next project is with Alameda County in Eugene, Oregon. They've partnered up with Caltrans and the PATH Institute at UC Berkeley to develop a magnetic-based guidance system. Their project is $1.9 million, and they're using it to outfit 3 buses. AC Transit is going to be outfitting 2 of their coach buses to run on an HOV lane across the San Mateo Bridge and through a toll plaza, as you see in the picture in the upper right. Lane Transit District is going to be outfitting 1 of their buses on their Emerald Express bus rapid transit. They'll be using the technology for a segment of the BRT corridor and also for precision docking at the station. Both of these projects are scheduled to begin in March of 2011. And finally, we've got San Diego. The San Diego Association of Governments received $18 million to begin a new bustle and shoulder service on a 20-mile segment of Interstate 805. Of that $18 million, 4.7 is going to be used to purchase 8 to 10 40-foot New Flyer buses that are going to come factory equipped with the vehicle assistance and automation technology in it. They're going to try and use an optical and radar-based guidance system similar to what Las Vegas tried, and it will also include what's called adaptive cruise control. The start date for this is still to be determined, although the latest that I've heard is that I think they're expecting to start it sometime in the winter of 2011. This service is going to be similar to the one in Minnesota in that the driver will be steering the bus at all times. The technology is only there to assist the driver and provide feedback. Also, similar to Minnesota, the buses in San Diego will only be using the shoulders when speeds in the general purpose lanes drop below 35 miles an hour. Now, the Federal Transit Administration has asked the National Bus Rapid Transit Institute, where I work, to evaluate these demo projects. Now, I need to be clear that it's not what we're doing. It's not a systems acceptance test or a components test. That's left to the transit agency and their system developer. What we've been asked to evaluate is the impact these guidance systems have on bus service. And we're going to look at 6 core evaluation areas. We'll be looking at customer satisfaction, bus operator satisfaction, efficiency and productivity, maintenance, safety, and technology performance. For each one of these core areas, we've developed hypotheses and measures of effectiveness. So, for example, in Minnesota, for the core area of efficiency and productivity, we have 3 hypotheses. We believe that the technology is going to facilitate greater use of the shoulder, higher speeds in the shoulder, and that it will facilitate greater on-time performance. Much of the data that we need for these hypotheses we'll be able to get from the onboard computer system. So we'll be able to compare the percentage of the shoulder length that was used when the driver was using the technology and when he was in the shoulder just driving manually. Likewise with the speeds. We'll be able to compare the speeds in the shoulders with and without the use of the technology. With the on-time performance, we'll be able to get that data from the AVL system. For safety, we'll be comparing the accidents per revenue mile for the evaluation year to the year prior. We'll also be comparing the standard deviation of speed in the shoulders with and without the use of the technology. In other words, do we see any evidence of the bus driver having to make abrupt changes in speed? For technology performance, we'll look at the average and maximum deviation from the ideal line, which is defined as the offset to the right of the fog line. Say, for example, the ideal line is set at 1 inch to the right of the fog line. We'll be able to check to see how well the bus stayed on that line when the driver assist system was being used and when the driver was driving manually. Similarly, we'll compare the number of steering motor activations. The steering motor is only activated when the bus is in danger of leaving the shoulder. And even when the driver is in the shoulder driving manually, the computer system will still generate a steering message. So we'll be able to compare the number of steering messages that were generated when the driver was using the driver assist system and when he was driving in the shoulder manually. I want to switch gears here now, and I want to briefly discuss some of the findings from an evaluation we did of Cleveland's mechanical docking arm. We looked at 4 areas. We wanted to know how precise was the docking, how fast was the docking, how much money was spent on damages related to docking, and how well the docking arm was regarded by the drivers. We did a comparative study between the Cleveland Healthline Bus Rapid Transit and the Eugene Emerald Express Bus Rapid Transit. The reason being that they both use the same model New Flyer 60-foot articulated bus. They both have elevated station platforms in the median. The Healthline platforms are 14.5 inches high. The Emerald Express platforms are 14 inches high. The major difference between the two is that the Healthline uses the docking arm, the Emerald Express does not. Instead, the Emerald Express stations are outfitted with a polyethylene guide strip, which you can see. That's the guide strip right here. Here's another photo of it. The guide strip sticks out 5.5 inches from the platform. Now, the guide strip, it's not a precision docking instrument per se. Emerald Express drivers are not supposed to make contact with the guide strip. It's simply there to prevent damage should contact occur. We had to identify comparable stations for the two sites. That is, stations with comparable roadway geometry, similar proximity to traffic lights, and passenger boarding on the same side. One set of matching stations was the Healthline's 9th Street station and the Emerald Express's Hilliard Street station. Both were median stations with left side boarding with a straight approach. The other pair was the Healthline's 6th Street station and the Emerald Express's Dad's Gate station. These two are median stations with left side boarding. However, both of these stations have a slight curve to the right just before the station, which is, you can kind of see it in the picture here. Let me highlight it. Right about here is where the curve is. As you're looking at the picture, the bus would be coming towards you. The first thing we measured was how close the buses were able to dock at the station. Now, our expectation was that the Healthline buses would dock closer because of the docking arm. For this, we measured from the same spot on the rear door, that is, the door behind the articulation point of the bus. In the picture on the screen, that's the left side of the bus. The next picture may better illustrate what I mean. This is looking towards the front of the bus. The arrow represents where we place the measuring tape. You can see from the photo that there's a slight difference in how close the bus gets to the platform before and after the articulation point. The front of the bus tends to be able to get closer to the platform, whereas the back of the bus sticks out a little bit. We did a day's worth of data collection at each site from 6 to 9 a.m. and 4 to 6 p.m. We had 102 samples of from the Healthline and 54 samples of the Emerald Express. The reason for the difference is that the Healthline runs every 5 minutes in the peak, while the Emerald Express runs every 10 minutes in the peak. So what did we find? At the stations with a straight approach, that is the 9th Street and Hilliard Street stations, on average the results were about the same. On average, the buses were 8 to 8.5 inches from the platform. At the stations with a slight curve before the approach, that is 6th Street and Dad's Gate stations, the Healthline buses did better. They were about 6 inches from the platform on average versus about 10 inches from the platform for the Emerald Express buses. That next column in the table, minimum gap, means that's the closest that we observed the bus get during the entire data collection. So, for example, the closest we ever observed a bus get at 9th Street was 4.5 inches. The closest we ever observed a bus get at Hilliard Street Station was 6.5 inches. Next, we compared how long it took the buses to dock. Our expectation was that the Healthline buses would be able to dock faster because the docking arm would take some of the driver stress away. We measured a distance 120 feet out from the marker where the buses stop. Now, in Eugene, they have a logo spray painted on the platform that shows where the driver is supposed to stop. In Cleveland, they either have a marker pole or a colored concrete paver. We measured 120 feet from that spot and marked it on the ground with chalk, as you can see in the picture on the bottom. The reason why we chose 120 feet is that that's twice the length of the bus. And it can be assumed that once the bus is 120 feet out from the stopping point, it's in docking mode. Using a stopwatch, we timed from when the bus crossed the chalk to when it came to a stop. We collected 75 samples in Cleveland and 55 samples in Eugene. Unexpectedly, we discovered that the Healthline buses took longer to dock, although in the grand scheme of things, it wasn't that much longer, about 5 to 7.5 seconds longer. What stood out in the data was the amount of standard deviation in the Cleveland data. While we were collecting the data in Cleveland, we noticed that there was a wide variation in approach styles by the drivers. Some would fly into the station and not even get close to the platform. Some would still come in quick and get close to the platform. Others would almost come to a complete stop before the station and then creep slowly forward until the guide wheel made contact with the platform. As bullet 2 in this slide shows, we think one reason for the wide variation in times could be driver experience. That is, some of the less experienced drivers may tend to pull in more slowly. With the Emerald Express drivers, there wasn't much variation in times. One reason for the faster, more consistent docking times on the Emerald Express could be that these drivers don't have to make contact with the platform. Another possible reason is that Lane Transit District offers a premium to drivers who commit to staying on the Emerald Express and give up their bidding rights on other routes. As a result, the Emerald Express tends to have more senior experienced drivers. The Healthline, on the other hand, is open to bid by any driver. In terms of damages, the cost spent per revenue mile between the two systems was comparable, 2 cents per revenue mile for the Healthline and 1 cent per revenue mile for the Emerald Express. Cleveland spent more money in terms of absolute dollars, but they also put out a lot more service. When we surveyed the drivers of the Healthline, over 80% of them agreed or strongly agreed that the guide wheel helped them to dock the vehicle more precisely, more quickly, that it was easy to learn how to use, and that they would recommend it to other transit systems. The only question that had a slightly lower percentage of favorable response was the one that asked whether the guide wheel made docking less stressful. I think the slightly longer docking times may be a reflection of that stress. But overall, I think the survey shows that the docking arm is still a highly favored tool by the Healthline drivers. And that concludes my presentation. It was a quick one. With that, I'll hand it back over to Dennis if there's any questions that we might have.
Well, thank you, Brian. If you have any questions, please click on the question and answer, the Q&A button that's up in the top center of your screen, and you can ask a quick question there. Right now we have one that asks about the Minnesota service operating on the in the swale in the emergency lane, and have they considered using the side view cameras that only protrude a couple of inches from the side of the vehicle? Brian, are you aware of Minnesota looking at using side view cameras?
No, I'm not aware of any plans that they have right now to use side view cameras, and I think the reason is because they've already made the effort to install the buses with the virtual mirror.
All right. Also, on the Cleveland docking arms, how much do those cost?
Staff from GCRTA, that's the Greater Cleveland Regional Transit Authority, they reported it costs about $3,700 to equip each vehicle with 2 docking arms because they have one on each side. So $3,700.
Another question we have is the services in San Diego and Rouen, will they be surveyed similar to that in Cleveland?
Oh, well, Rouen, no, we don't. We're not doing any evaluation of the one in France, but I wish. But yes, we will be doing. We're doing individual evaluations for all those pilot programs for the San Diego, the Minnesota, and the one in Eugene and Alameda, and we'll be coming up with measures of effectiveness and hypotheses for every one of them.
All right. Amy Datson at our Florida Department of Transportation asked about ADA and the gap between the bus and the curb. Have we looked at that from an ADA sense?
Yeah, that's a very good question. I'm glad she brought that up. That was an issue that Cleveland had to work through with FTA. In addition to the only way that Cleveland was able to get permission to use the docking arm was to agree to, in addition to that, install special ramps that would come out from the door as a backup in case there was too much of a gap between the bus and the platform.
All right. You mentioned about the Las Vegas Max BRT and the optical guidance, but they discontinued it. Can you give us a little more? I know they say what happens in Vegas stays in Vegas, but can you give us a little more information on why they canceled that service?
Yeah, just to elaborate on what happened there, they discontinued use of the optical guidance system because of the extensive maintenance requirements to keep the pavement markers clean. Remember, the way that system works is the cameras look at the stripes and they lock onto a trajectory, but it can only work if the cameras can detect the stripes. In other words, they have to see the contrast between the stripes and the pavement. What was happening out there, because of the desert environment and low rainfall, dirt was constantly accumulating on the pavement markers, and the cameras were not able to read the contrast between the stripes and the pavement. So as a result, the cameras could not lock onto a trajectory. Now, San Diego they have plans to develop an optical-based guidance system, and conditions in San Diego aren't quite the same as they are in Las Vegas, so I'm assuming that they think they're going to have better luck than Las Vegas did.
All right. Any other people who have a chance here to ask some questions and answers, get some answers from Brian? Just click on that question and answer in the button in the middle up there. You can submit your question. Another question, Brian, we had was about liability and warranty issues with these technologies. Can you share that with us?
Yeah. The Minnesota Valley Transit Authority, the ones developing that GPS-based guidance system, they did have to resolve liability issues with their insurance provider. They're not self-insured. They have a private insurance provider. And that provider was worried that the technology would make the operations in the shoulder more dangerous. So MVTA and the ITS Institute were finally able to convince the insurance provider that the technology would in fact make operations safer. I think they had to show the provider the training that the drivers went through. They showed them the bus simulator that they had developed, and they explained that the driver would still be in control of the bus at all times. I mean, the driver would always have his hands on the steering wheel. The driver assist system was only there to provide feedback to the driver. So it was something that they had to work through. Cleveland, on the other hand, it wasn't so much liability issues, it was warranty issues they had to work through. The only way they could convince the manufacturer of the axle and suspension system to install the docking arm was by agreeing to waive the warranty. Before the Transit Authority could do that, though, they had to convince their own internal legal staff that the risk of waiving the warranty was minimal. They made the case, and their legal staff agreed that the amount of torque that would be put on the docking arm would be less than the torque put on a front axle of a snowplow truck, which is considered normal and acceptable for liability purposes. Once those hurdles were overcome, the docking arms and guide wheels were manufactured and installed, but Cleveland did have to waive the warranty.
Okay. I guess with no other questions being asked, any last chance? I'll remind you that the program was recorded today. You can get that from our CUTR website early next week. Also, in the upper right-hand corner of your webinar screen, you'll see what looks like 3 sheets of paper. You can download Brian's presentation from there. So that's in addition to the recorded webinar. And I guess we thank you all for attending today, taking time out from your lunch or a brunch, depending on where you are in the country. Our next webcast will be on December 2nd, and the topic will be motorcycle crash trends in Florida, which will be presented by Chan Young Lee. We'd like to take a moment before you log off for you to complete the evaluation form for this seminar. We'd really like to get your feedback on how informative these webcasts are to you. And with that, we thank you very much for your attendance today. And have a good day and a good holiday next week.